Hello everyone, and welcome to another AP Computer Science video. Today we're going to continue with our recursion examples. Last time we talked about the idea of recursion, where we have a method that in its definition calls itself, which initially seems counterintuitive, but if we follow certain rules we can use this to our advantage to write simplified code in a way that's easy to read and generally easy to understand. And if you don't remember, the three main components of any recursion, the three things that we should have in a recursive implementation are the following. A base case, a situation where the problem that we're trying to solve with our method is known without any effort, without recursion occurring. In our example of factorial, we said that for the factorial of 1 and 0, we know the answer is 1 immediately. The second thing is the simplification of the problem. Whatever the problem happens to be, before the recursion occurs, or when the recursion occurs, there should be a smaller problem to solve. If you are trying to solve the same problem again and again, then you can never make any leeway towards finishing it. So usually the simplification of the problem means shrinking the problem in some way, moving towards a base case, right? And the third step is the actual recursive call. And so in our example of the recursive factorial, we can see that eventually we do call fact rect in itself, and that's our recursive step. So today we'll do a few more examples of recursion. For common problems, again, these are problems that maybe we could do with iteration, but to see the approach recursively, we should be comfortable with this idea and how we can use it to our advantage. And sometimes it makes sense to do things in a recursive fashion, though it is not necessarily something we ever really absolutely must do. So I'm going to shrink some of these problems, and we'll make a new example. So we'll start off with the problem of counting, let's say, the number of even values in an array list of integers. So we have a list of numbers, and I want to say how many evens are in this list. Right? This is a problem that we would easily solve with iteration, with a loop or for loop, an enhanced for loop, something very, very simple. But I want to try it with recursion just to see how we can move through, or what looks like move through, a list of items. And so the way we're going to do this in two steps. And again, this is just a different type of approach. This is not the only way to solve the problem, and it's not the only recursive way to solve the problem, but it is an approach that is often taken because it allows us to break apart the problem into the kind of components we want to recognize. So we'll make a method. We'll say public static int count evens. Our input is an array list of integers. We'll call it list. It's going to ask us to fix imports. We'll do that. And now notice that my input is only the list itself. What I want to do is to solve this problem, I have to come up with a recursive solution. And the approach is going to be the same as going through the list iteratively. We're going to move one index at a time. But the difference is the recursion is what's going to move the index. We're not going to use a loop to make this happen. But for this to work, when the recursion occurs, the input to that function, unfortunately, is just a list, so we don't really know what index we're going to be at. So what we're going to do is we're going to make what's called a helper method. This is a method that is only intended to be used within the count evens, and it is the one that does the actual recursion and does the heavy lifting. And so here's the example we're going to make. We're going to go ahead and do this. We'll say, and we'll even put it private, even though it's not going to change anything in this example, but we'll put it private to give the intention that this is not meant to be used by other people. It's only meant to be used by the count evens method. So we'll call it static int. We'll call it count evens rec. Our input is an array list of integers, the same list. But now we're going to add extra parameters, and this is why a helper method is helpful, because if they told us I need to make a method that only accepts a list and then returns a number of even values, the helper has no such limitation. The helper can have any extra data we might think is helpful. In this case, where we are in the list currently, the index through the recursion of where we currently are. This is very much like a sentinel value that we have in a for loop. So we'll call int idx. And so now I'm going to go and simplify and return the answer to this one very simply. I'm going to say the public-facing method, the one that everyone's going to use, is simply going to call the helper. So here we go. We're going to say return whatever the recursive version does. So count evens rec. And I pass in the list. And if we ask ourselves, if we were to iterate through this list, looking at all the values, where do we normally start? Typically, we start at index 0, so it would be a good choice to say start at index 0. And so there it is. So again, the assumption that's being made here is that this thing relies on the recursive version. Right? So helper methods are often very helpful because recursion sometimes needs more data than we might be asked to use, and so we can kind of hide it behind the scenes through our helper method. And so now we can ask ourselves, what is the base case? What is a situation where we know the answer immediately to the question of how many evens are in the list? And there might be more than one question, but I'll think of one, and you might have your own answer to this, and so we can think about this for a moment. I will say, I think one reasonable base case is if the index is beyond the size of the list or equal to the size of the list. So for example, if there are 5 items, the indices would be from 0 to 4. So if the index happens to be equal to the number 5, then in this example of 5 items, then the answer is 0 because you're beyond the safe index of the list. That's one solution. We could also maybe check, well, if you happen to be the last index, then we simply need to check, are you even or odd? And if you're even, then you can return 1, and if not, you return 0. Because in both cases, we know the answer. If we're at the last index, we're at the last item, and the item is even, then there must be 1 even. And if the last item is not even, it's odd, then there must be no evens, 0 evens. So either one of those is acceptable. We can go beyond the list and say, if you're beyond the list, the answer is always 0. And if you're not, then you might check. And I'm going to do it that way just because I think it saves me a little bit of effort in terms of writing our if statement. So here's my base case. If the IDX is greater than or equal to list.size, then I know the answer is 0. Right? The index is beyond the safe index. Right? So if the index is beyond the last safe index of the list, then the answer must be there are no evens in that thing. Right? And this is actually nice because it works out for a list of size 0. If the list was size 0, an empty list, then the 0 would be greater than or equal to 0, and therefore the answer would be 0. There's no evens in a list of 0 items. Right? So that works out nicely. Now, otherwise, we need to shrink the problem. The problem here is simply, are we even or not? Is the current item even or not? And then if it is, we add 1 to the answer, and then we recursively count the evens on the rest of the list. And if it's odd, then the answer is just however many evens are on the rest of the list. So that's what we're going to do, is we're going to have 2 situations here. That is the current value at IDX even. So here it is. Right? If list.get IDX mod 2 is 0. So if it's even, then what is our answer? We know that the current one is even, so that's 1, plus the recursive counting of all the evens in whatever's left over in the list, from the next index to the next one, and so on. And so again, when we do our recursive call, what we can do is let's assume it's going to work correctly. And if so, then we can finish up our work. So the answer here is simply 1 plus however many are after this point. So here we can do our recursive call, count evens rec on the list, and IDX plus 1. Why? Because this index is moved over by 1, and we'll come back in a moment and describe everything, but let's finish it off. If this is not true, that would imply that it's an odd number. And therefore the answer is simply the even recursive counting of the even numbers on the rest of the list. So we can do the same thing, count evens rec list IDX plus 1. So either this one's going to happen, because it's a return, and it's going to recursively solve, or this one's going to happen. Either we add 1 for the current even, or we don't. And then each layer of recursion will add 1 or not. And there's some result will be a total of however many evens there are. And so if we ask ourselves, did we cover all 3 components of our recursion? The answer is yes. Our base case, we're beyond the size of the list, we're beyond the safe index, therefore our answer is immediately 0. That's our base case. Our shrinking of the problem. In our recursions, the shrinking of the problem is implied by the increase of the index. Every time we move the index, we're getting closer and closer to the size. Eventually, IDX will be big enough where this will be true, our base case will be triggered. And then the recursive step, and here it is, the calling of the method on itself on that adjusted problem. So let's test this out and see if this does work. So here we go. Let's go to our main. Let's try creating a list. So we'll do this. We'll say list is equal to a new array list. Numbers. Let's just add some numbers. List.add 5. Actually, let's do this better. Let's do random numbers. We'll do 10 random numbers. Actually, let's do this. Let's do this so it's much more readable. We'll say int is equal to so we'll do numbers between 0 and 10, and then we'll add r to our list, and then once we're done, we will print out the list. So we'll print out list, and then we'll print out the number of evens based on our recursion. Again, we're not going to call the recursive version. We're going to call the public version count evens. So count evens, and our list is our input, and there it is. So let's see what happens. Oh, I have a, and there it is. Oh, this was because this was taking a bit of time. I forgot that we had this big Fibonacci number. But there it is. So let's count how many evens there are. 1, 2, 3, 4 evens. And there it is, 4. So let's fix this real quick. I don't want my Fibonacci too high. Let's put a really fast number and let's run it again. And there it is. 6 even numbers. 1, 2, 3, 4, 5, 6. Let's run it again just to make sure. And there it is. 1, 2, 3, 4. So we have 1, 2, 3, 4, 5, 6, 7. So let's do one list test. Let's go ahead and do no numbers, so an empty list, and we should still get 0. There's nothing in the list, and there are 0 even numbers. Let's put 1 and just see if it's possible to get an even or an odd number. There's an odd number. There's an odd number. There's an even number. So it seems to work recursively. I hope that makes sense to everybody. The base case, our shrinking of the problem, in this case, is moving the index along in the recursion, and then the last step is the recursive call itself. So let's do another example with recursion. So our next problem is going to be this. Given a string, return a new string that contains none of the vowels that were in the original string. So if we have the word hello, H-E-L-L-O, and we call our method, it should recursively remove all vowels, and we should end up with the string H-L-L. So we're going to try to do that, and again, with recursion, I mean, with iteration, we could have probably done this without much effort. It's something that's not too challenging. But with recursion, it's also the same problem, but the approach might be slightly different, and how we decide to get things to work is the real approach to this situation. So here we go. Let's make a method to make this happen. In this situation, we're not going to make a helper. I don't think it's necessary. We maybe could, and in reality, it would be very similar to the list problem because strings, if we think about them, we've used indices to retrieve individual characters, and so it is quite possible to do this. But it really depends on what our goal is. And in this one, I'm going to try to take the approach of not using a helper method. And it may not be the most efficient, but that's not really the goal here. The goal is just to do it recursively. So we'll say public, we'll say static, and it returns a string. We'll call it remove vowels. So string is our input. And so again, the approach we need to take, we'll take a minute to think about it, is what is the base case? What is a scenario where we know the answer immediately? And there might be more than one, and there might be more than one that's a good choice, and we have to decide what's the best a thing to do. It's not always an obvious answer to what's the best approach or what's the best base case. There might be more than one base case. It's quite possible. So I'll try one. I think one good base case is if the string is empty. If the string is empty, we know the answer. An empty string that contains no vowels or consonants, when we remove all the vowels, is an empty string. So we can try it like that. We can say if str is equal to an empty string, then we can simply return. We can return a literal empty string, or we can just return str. They're all the same. It's either one is acceptable, but we'll return it immediately. That's my base case. Now, the shrinking of the problem and the recursive call is the approach that might take a little bit of thought. And so what does it mean to shrink this problem? Well, we're going to have to decide, well, which character am I looking at to decide if it's a vowel or not? Because I'm choosing not to make a helper that contains an index, I have to decide, well, which character should I look at? And so the approach I'm going to take is I'm always going to look at the first character. But that would imply that when I shrink my problem, the string that I give the new recursive call, that smaller problem, can't be the same string. It must be manipulated in some way to shrink the problem. And in this case, get it closer to my base case of an empty string. So the approach that we're going to make an effort to solve is to check the first character. If it's a vowel, then we don't include it in our answer. If it's a consonant, we include it in our answer, and then we recursively solve on a string that doesn't include the first character, because that way the recursion will check the next first, quote-unquote, first character. It's always going to change the first character. So let's go ahead and do this. Let's go ahead and say if the first character, so substring from 0 to 1, is equal to, and actually let's make this a little bit more efficient. Let's do string first is equal to, and we'll take this part right here. Let's go ahead and copy it or cut it and say that's the first character. And if the first is equal to an A, or, and now I'm going to be lazy and I'm going to copy this again. It's equal to a E, or an I, or an O. And let me go ahead and put this on the next line, even though it's going to look ugly. Or a U. So if it's one of the vowels, A, E, I, O, U, then we do not want to include it in our answer. So what is our answer going to be? And I'll put curly braces here just to make it a little bit easier. The answer is going to be whatever the recursive adjustment or the recursive answer is to this problem. So we can simply say, you know what, that first character is a vowel, throw it away. So the answer is the recursive solving on the rest of the string. So we're going to return the recursive call remove vowels on the rest of the string. So how do we get the rest of the string? It's going to be from 1 to the end. And there it is. So notice that first character was thrown away. We didn't refer to it again. It's gone. And every recursion that we find the first character being a vowel, we throw it away. So theoretically, the problem will shrink, shrink, shrink. If it's all vowels, we'll end up with an empty string. Now, if that is not true, it's not one of the vowels, then our answer is almost the same. In fact, it's basically the same, except we don't want to throw away the first character. We want to keep it and reattach it to the recursive solving of the rest of the string. So if we had the word high, H-I-G-H, we would say, okay, we'll take the H off, recursively solve on I-G-H, which if we assume works properly, we'll get G-H as an answer, and then reattach the first H to the G-H, which ends up giving us H-G-H. So we're going to say, you know what, the answer is the first character, which we don't want to throw away, plus the recursive solving of the rest of the string. And again, we have all three components. We have a base case of an empty string, which handles an empty string and other situations. We have the shrinking of the problem, which is always going to solving on a string that's one character shorter than it was, and then the recursive call. Again, is there another approach? Sure. Could we have made a helper method that had an index? Then we could move along as if it were a list. Yeah, we could do that way too. That's not unreasonable at all. But I think this approach is just a different view of things. And it's not necessarily the most efficient because we are creating new strings every time we concatenate and call substring and so on. So this might take up more memory because of all the string references and objects being created, but if we're not worried, then that's not a terrible choice. So let's test this out and see if this actually works. So here we go. We'll make a string. We'll start off with the first string we had said, hello, and there it is. And then let's go ahead and print out the recursive call of remove vowels on hello. So we should get, hopefully, H-E-L-L-O. I mean, we should get H-L-L. So let's see what happens. And there it is. The E and the O were removed. Let's test this out. Let's do ABBA, ZABBA. And so we should end up with BB space ZBB. Let's see if that works. BB, ZBB. There it is. And let's do one more. Let's do an empty string. And we should get an empty string back without a crash. And there it is, an empty string. Let's do a single letter, which is a consonant. We should get that single letter back, and there it is. And let's do a single letter that is a vowel, and we should remove and get an empty string. And there it is. Looks like it's good. We'll do one last test. So we should end up with JMB, JNS. And there it is, and notice it does not consider. Now, this is a situation I know is not going to work, so let's try this. Unfortunately, I'm going to end up with the word James as an answer. That's a problem because I forgot to ignore capitalization. So let's fix this. Instead of saying first equal to A, let's say first dot to lowercase. But now the problem is this is going to wipe out what it was, so maybe we should do this. Let's go ahead and do this. Let's do this. Make a small adjustment. We'll copy this one. First is the original, and then now in our comparison, we're checking lower against all the lowercase versions. So our comparison is now ignoring our capitalization, but our answer keeps the original letter capital or not. So this works out, I think, slightly better. So now our test on James with A and E should end up with capital JMS. And there it is. And we can do it one more time to prove that it still works with lower cases. James. We'll do a mix. So the A and the E should still both be removed. And there it is. So I hope we see that recursion, again, could we have done this with iteration? Absolutely. But recursion does have its purposes. And again, we're not really in a point in our programming where the recursion is necessary. For the AP exam, you should be able to read code and determine what's happening. We'll see some examples on the College Board website of their kind of questions they ask. You're not going to be required to solve a problem with recursion, even though you might be able to. But it's not going to be a strict requirement on the exam. They've never done that. And so it's not too important that you are perfect at this skill. It's one that you grow into. It's definitely a more challenging aspect. We'll in our next video, or pretty much our last video on recursion, we will see two examples of recursion in real-world scenarios. One that we've already seen, the binary search, and then one for a sort that is significantly better in terms of its performance than the other sorts that we've seen because of its recursive use. So I'll see you in that next video.